It couldn't be more important. This, like I said, this is really the heart and soul of what finance is all about. So basically what it refers to is the idea, very simple idea, that a dollar received today is more valuable than receiving a dollar in the future. Why is that? Because the sooner you receive that dollar, the sooner you can invest it and earn interest. So interest is what's going to determine how valuable a cash flow received in the future is. So the time value of money will help us understand how to compare the cash flows received at different points in time. So we're going to have four basic concepts here. The future value of a sum, which means a one-time only payment. The present value of a sum, again, is a one-time only payment. The future value of an annuity, which is a repeated series of equal cash flows. And the present value of annuity, okay. So future value in a nutshell means how much is an investment worth in the future. The present value is the opposite. It means how much will a future investment be worth to us today? Okay, so we can apply it to a single sum or an entire annuity. Many financial products are structured as annuities, which is why this is so important. So we're going to do this in a few different ways. We're going to see how to do this algebraically, and then we're going to see how to do this with Excel. Okay, and then we can also see how it's done on the TI-84 if you're interested. You don't have to do it, but I think it's a good idea if you own one to learn how to use the financial applications built into it. And yes, they're in there. You may not have known it, but they're in there. All right, so we'll start with the future value of a sum. Now, if a sum is invested today, it will earn interest and increase in value over time, of course. The value that it grows to is known as its future value. Computing the future value of a sum is referred to as compounding. Okay, so yeah, I mean, you can imagine how this would work. Let me write this out on a separate diagram. So we often use a special diagram, which is called a timeline, to illustrate these types of time value money problems. All right, so I'll create a separate document here so I can make more notes, and I'll post these later on when we're done. So, for example, let's say and by the way, on this timeline, we often show on, it doesn't really matter whether it's the top or the bottom. I usually put the time in the bottom. Those numbers represent time, meaning that this is today. This is 1 year in the future. And this is 2 years in the future. And these don't have to be years. They could be months or days, whatever the case may be. So on the top of the line, we'll have cash flows. Now, the important detail here is that cash flows that are coming into our pockets are shown as a positive number. The ones that are going out of our pockets are shown as a negative number. So today, imagine I put $1,000 in the bank. So I'll show that with a negative number. And then in 2 years, it's worth, let's say, $1,150. Okay, so now we're assuming that I left the money there the whole time. I never took out any of it in between. So what I can say here in this example is that $1,150 is the future value of $1,000. And we can also turn that around and say that 1,000 is the present value of $1,150. Okay. So what that means then is that in principle, if you had your choice, you would be indifferent between receiving $1,000 now or waiting 2 years to receive 1150, because in investment terms, it's the same thing. Okay. So the question is, how do you go from 1,000 to 1150? Well, in order to answer that question, we need to know the rate of interest. Right. So you'll see interest rates are going to be the driver of everything in this section. Okay. Now, interest rates, as you know, are determined in the marketplace through the activity of buyers and lenders. And it's a very complex topic, and we'll be discussing a lot of it as we go along. But we're going to make some simplifying assumptions here. We're going to assume that I can put my money in some investment, let's say it's a bank account, and get some rate of interest, and that will let me determine how much I'll have in the future. So in this case, we're going to see our first equation of the course. Let's see what this is all about. All right, so well, two of these should be pretty straightforward. And the notation here, by the way, is I'm pretty sure, if I remember correctly, this is based on Hull's book. FV is future value. E is the present value. R is the rate of interest. And N is the time over which P is invested. And that it might be in years, but it doesn't have to be. Okay. So the interest rate, by the way, just as an aside, interest rates are always quoted on an annual basis, which means if it says 3%, it means 3% per year. All right, so that's understood. Also, in an algebraic formula like this, we always represent interest rates as a decimal in algebraic formulas like this one. So there's 3% would be written as 0.03. Okay. These formulas, any formula you run into in finance, it is not going to accept a whole number like 3 for 3%. It's going to ask you for 0.03. So let's just use a quick example. Let's say, suppose that $1,000 is invested let's say for 5 years at a rate of 4% per year. So you put the money in the bank, you leave it there for 5 years. At the end of 5 years, you come into the bank and say, how much do I have? And they'll look at it and say, oh, here's how much you have. Here's your balance. That would be the future value of the $1,000 invested today for 5 years at a rate of 4%. So based on our formula, oops, so it's 1.041 plus the rate of interest. The rate of interest will be expressed as a decimal of 0.04. We add 1 to that. The exponent is 5. And let's see. Now, for this, you will need a calculator. And of course, the answer will be rounded to dollars and cents. That's the future value. So in other words, in 5 years, my balance will be 1216.65. And of course, it should be obvious that of this, 216.65 is my total interest. Okay, so now it turns out, we might as well discuss this now because it's going to be important. There are two basic kinds of interest that I've just earned. Okay, it's true that I made 216.65, but we can break this down into two other types of interest. Interest can be earned from two different types of interest. Let's put it that way. We have what's called simple interest, which is interest on the invested principal. And we have something called compound interest, which is interest on interest. Now, what does that mean? All right, well, what's going to happen is that every year that goes by, in fact, I'll tell you what, let's do this. Let's figure out, although this might take a while, I guess, how much interest we're earning every year from this account. All right, so let's try this real fast. At the end of the first year, we're going to have 1,000 times 1.04, because remember, it's 4% per year. Okay. Now, clearly, $40 here is our total interest. Because all 4% of that was based on the original principal, all 40 of that is what we're going to call simple interest. There's no compound interest. Not yet. Now, at the end of the second year, we're earning a 4% return, not just on the original $1,000, but on 1,000 plus the $40 interest we earned in year one. So that's going to bring my balance to $1,081.60. So if you notice, during the first year, I earned $40 worth of interest. During the second year, I earned $41.60. Where did that extra amount come from? Good question. So altogether, I've earned $81.60 in total interest. Now, 4% for 2 years times the original principal of $1,000 is $80. That is simple interest. And that will never change. In other words, I'm earning $40 a year in simple interest, which implies that the rest is what we're going to call our compound interest. Or if you're not sure, what you can also do is think of it as 4% of 40, the interest earned during year one, is, as you'll see in a second, what do you know? 4160, which means 1.60 is the interest, and it is specifically the compound interest. So that last $1.60 is based on the $40 of interest we earned during year one. Altogether, we have $80 worth of compound interest. So let's look at year three. Well, I'm sure you can guess where this is going. We're going to have another $40 in simple interest, but we're going to have even more compound interest. So our new balance is $1124.86. And now we're running desperately short on space here, but I want you to notice that of this $124.86 in total interest, 40 times 3 equals 120 is our simple interest. And the rest is our compound interest. So let's just carry on. Let's go all the way out to year 5. We have 1,000, as we just saw, brings us to 1216.65. Now, how much simple interest does that represent? Remember, it was $40 a year. 200. Oh, actually, what I should have done, hold on one second. Is it just right here, the total interest is, of course, 216.65 because we started with 1,000. The rest must be the interest. So the simple, as we've discussed, is 200 because it's $40 a year for 5 years. The rest is the difference, which is 16.65. Now you're probably saying, well, that's not much, it's not that it's not worth worrying about, but it's a very small percentage of the total. But what's going to happen here is that over time, if you were to plot out the simple and compound interest as the years go by, and as years in this case, their simple interest grows like this. It's a linear function. The compound interest, on the other hand, accelerates over time. In fact, in the limit, we'll discuss this later on, but in the limit, it grows at an exponential rate. So if you're saving money for retirement, let's say you put money in the bank for 30 or 40 years, by the time you retire, the vast majority of that money will come from compound interest. Okay. As you leave the money long enough, it really grows very, very, very quickly, but it takes a long time to get to that point. So, no matter what investment we're making, it should be easy to determine, first of all, the future value. Now, of course, if you notice, this is a simple case, the interest is the same every year. That's not such a big deal. If you're investing your money in something like a certificate of deposit, which, if you don't know, it's a special type of savings account. Whoops, hold on. Oh, I just realized I never saved this document. I better do something about that right away. You know what's going to happen if I don't? My electricity will go out for 1/10 of a second and my work will be lost forever. So by the way, I'll be posting all this on a Blackboard when we're done. So if you miss something, you'll have a copy of this. Anyway, so yes. So compound interest, simple interest, total interest. Those are three very important concepts for us to keep in mind when we analyze these investments. And so we can figure out the future value from this formula. The simple interest, it's just a question of multiplying out the percentage interest the principal that we're multiplying it by, and then the number of years. So in other words, the simple interest using this notation would be P times R times N. That's all it is. Okay. Whatever's left over is your compound interest. All right. So this is a good start. Here's the example I had in the slides. We have the sum of $1,000 invested for 4 years at an annual rate of interest of 3%. What is the future value of the sum? All right, so we'll do the same thing. We have N is 4 years. 3 is the rate of interest, which you notice I've converted to a decimal. And then the principal or present value is $1,000. Multiply those out on your calculator, and you'll see that it's always rounded to dollars and cents. We end up with 1125.51. Now, you know how to determine how much of that is total interest, simple interest, compound interest. So I'll tell you what, let's figure that out right now. So first of all, let me add some page numbers here. All right, so remember the details we had. So you can take that out, you can take out your calculator and solve for that directly. And you'll get, yes, 1125.51. Now, of course, obviously, the last 125.51 is your total interest. That's the easy part. So the total interest, it's going to be the future value minus the principal. Now, remember, I mentioned earlier that the simple interest is the principal times the rate times the number of years. 1,000 times 0.03 times 4, $120. So whatever's left over must be the compound interest. Move that back. So the difference, so I put the little negative there. The compound interest is the rest, which is 551. And again, for such a short time frame, the vast majority of this interest is simple interest, but that will change over time. After enough time goes by, eventually it'll be the compound interest, which is the majority of the rate of return. Okay. And then here, it discusses the difference between the two. Now, what if we want to do this in reverse? Imagine yourself saying, I need to save $10,000 in 4 years to buy my dream car or something like that. The question is, how much would you have to put in the bank now in order to ensure that you have the right amount in the future? Another way of thinking about it is that if I had a choice between receiving $1,000 in the future and let's say $850 today, would that be which one would I pick? Or at what point, How much would I have to receive today to be indifferent between having that sum now and $1,000 in the future? So what we're going to do is calculate the so-called present value of a sum. And it turns out that this is awfully important because all securities in the marketplace, stocks, bonds, whatever you may be thinking about, ultimately their value is nothing but the present value of their future cash flows. So you can see why I said before, this is really the foundation of all of finance right here. The time value of money is the bedrock on which finance sits. Okay. So algebraically, you can probably guess what's going to happen. We're going to invert this formula and solve for P. All right, make this just a little bit bigger. So if you rearrange this algebraically, this implies that P equals FV over 1 plus R to the n power. All right, so let's look at the case in front of us. Let's say we want to know how much would we have to put in a bank now. It pays an annual rate of interest of 5% in order to be worth $1,000 in 3 years. So it's a 3-year investment. We're aiming for $1,000 in 3 years. That's our future value. And then the rate of interest is 5%. So it's a simple matter of plugging this in. Whatever this number is, clearly it'll be less than $1,000. The question is how much less? It's 863.84. So that implies that over the next 3 years, I will be earning interest equal to the difference between these two. And that's going to be 126.16. Nope, sorry, it's 136.16. That's what I get for doing it in my head, I tell you. Okay, so that means by saving, I'm earning 136.16 worth of interest to guarantee that I'll have my $1,000 in 3 years. So, or think about it as in terms of investments, having 863.84 now is equivalent to having $1,000 in 3 years. And now one thing that we did not quite get around to analyzing is what happens when the interest rates change? What happens to the present and the future value? All right, so actually, I guess my intention is to have these sessions last for roughly an hour each. So I'll tell you what I'm going to do. Let me add this to the bottom here so we don't forget about it. What I'd like to be able to do is show you the relationship between the rate of interest and the present and future values. In fact, we could go into Excel and create a nice little chart so you can create a graph and see how these are affected by different interest rates. So how are PV and FE affected by interest rates? Well, you know what? Maybe we can do it right now. Hold on one second. This shouldn't take too long. Let's go back to the previous example for future value. N is 4, R is 3%, and P is 1,000. And the future value, we can do this algebraically, is P times 1 plus the rate of interest raised to the n power. And rounded to dollars and cents, as we saw, it's 11.2551. So what I'd like to do now is create an entire table of these results where only the interest rate is changing. Actually, I'll put R out here. R and P all right, it goes all the way up to 27. We don't really need that much. Let's stop it at 25%. And so I'll use that formula, equals P over, P times 1 plus the rate of interest raised to the n power. And so what I'm going to do now is insert a graph. And you'll see that it's not a linear relationship. So in other words, as the interest rate goes up, that would be our independent variable, or x. The future value is the dependent variable, or y. And if you notice, it's increasing, but not at a constant rate. It appears to have a first and second derivative that are both positive. Okay, so what about the present value? So the example on our slides is this. N is 3, future value is 1,000, and we're looking at a 5% rate of interest, and the PV turned out to be $863.84. So we're going to set up a similar chart here. Except this time, I'll reverse these two. So we'll let R be everything. We'll go up to 25%. N is 3. PV is 1,000. So for this, we have 1,000 over 1 plus R raised to the n power. And then I'll grab these two columns. Well, that's strange. I guess it, well, it worked before. Oh, what was the holdup? So anyway, it goes down. That's the bottom line, but it's not a straight line, is it? It's curved. We'll discuss the consequences of that later on. It will be an important detail when we're looking at the management of interest rate risk. This relationship between prices and present values, sorry, rates and present and future values. All right, let's see. Just to be consistent, I'll call this future value. All right. So I think that was kind of helpful. So, Eric, yes, anyway, so we'll cut it off right here. The next time, we'll just carry on with this first section. We've got a lot of material to cover here, by the way. Um, we're going to introduce this concept of compounding frequency, which is a hugely important idea. So we'll save that for next time. And so we're getting into some very deep waters here, as you can imagine. So for the first session, that's quite enough, I think. So next time, we'll get involved in compounding frequency. So I'll see you then. So what is this all about? All right. Well, every example we've looked at so far, and we've talked about present and future value, was based on a simplifying assumption that interest is actually credited to our account once a year. Okay, so that's usually not the case. So what we're going to consider now is this notion of compounding frequency. So what does this tell us? So when investors earn interest on, let's say, in a bank account. Let's keep it simple. The bank may pay interest on an annual basis. For example, if a bank pays a 4% interest per year, then if interest is paid on an annual basis, the investor will receive 4% at the end of each year. This is known as annual compounding. Now, what if instead the bank pays half of the annual amount twice a year? If instead the bank pays 2% twice per year, this is known as semi-annual compounding. How about this case? If instead the bank pays 1% 4 times per year, you can probably guess this is known as quarterly compounding. So you're probably wondering, well, what difference does it make? Well, it can make a significant amount of difference. So if you're the investor who's earning interest, it turns out that you would like to see the interest compounded as often as possible. So why don't we do a numerical example and see why when we have annual compounding, and let's assume that the investor starts out with $1,000. And the interest rate is 4%. Let's keep it there. Okay, so with annual compounding, at the end of the year, the investor will have. All right, and so for this, let's go back and revisit our formulas that we saw last time. So for future value, we have P times 1 plus R to the n power. And remember, P is the principal. In this case, that would be $1,000. R is the annual rate of interest. Well, actually, I'll just express it as the rate of interest. The frequency of the interest rate depends on the problem. So I'll just refer to it more simply as the rate of interest. N is the time until, or I guess I should say, the time until the maturity of the deposit, meaning that if you mean to leave the money there for a year, then N is 1. And of course, FV is the future value. All right, so in this part, P is 1,000, R is 4%, and N is 1 because it's a 1-year deposit. Actually, I forgot to mention that in the beginning. Let me add that right now. 4% annual rate of interest for 1 year. Okay, now we're all set. So $1,000 is the principal. The rate is 4% per year, and it's 1 year for which we'll keep the money in the bank. So we know how to do this already. FV equals 1,000 times 1.04 to the first power and of course that means that $40 is the interest that we earned. Now, we did discuss last time the distinction between simple and compound interest. Simple interest is only based on the amount of principal involved. And so we normally calculate it by multiplying the principal times the rate times the time frame. So in other words, you would have PRN, which is 1,000 times 0.04 times 1, which is 40. And so because they're equal to each other, that implies the difference is the compound interest. And in this case, that would be 0. Now, this is where it gets interesting. So we'll think of that as part A. In part B, we're going to change the compounding frequency to semi-annual. Okay, so here we're assuming annual compounding. In part B, we're going to assume semi-annual compounding. Now, that means we have to make some changes in our formula. But before we do that, I would like to show you exactly what's happening here. We, instead of having a deposit and at the end of the year receiving $40, in fact, let me sneak in a little graph here. The timeline for this problem in part A looks like this. All right, so we went from 1,000 to 1,040. Okay. Now, with semi-annual compounding, what's going to happen is this. We start with a deposit of $1,000, but at the end of 6 months, we will actually be paid half of the annual rate of interest, which is 2%. So here, the amount of money we have in our account is now, if you notice what we're going to do here, the interest rate is going to get cut in half because it's only 6 months. So we're going to have $1,020. Fine. Okay, now what about at the end of the year? This time the principal is not 1,000, but 1,020. So we're actually multiplying 1,020 by 1.02. That's 1,040.40. All right, so you can see the difference already. We started out with $1,000 in principal. The total interest must therefore be 4040. Now, the simple interest is completely independent of the compounding frequency. So therefore, the simple interest will always be $40. Sorry, 40 cents. No, $40, but 40 cents is the compound interest because that's the difference. Okay, 40 cents. It doesn't sound like much, but it grows like crazy over the years. Okay, in other words, you'll see later on that this is where the majority of the return to a long-term investment comes from, as long as the time frame is sufficiently long. Not for a couple of years, not for 5 years, maybe not even for 10 years, but eventually it'll get to the point where we're earning more from our compound interest than our simple interest. Now, with the quarterly compounding, we're getting paid 4 times a year. So you start with 1,000, and then every quarter you get another payment. Now, this time, instead of getting 4% per year, you're getting 1% per quarter. So this future value will be 1,000, 1,010, and then here we're going to have 1,010 times 1.01 to the first power. And let's see what that gives us. $1,020.10. And so you can see we're running out of space here. At the end of 3/4 of the year, or 9 months, that is now 1030. Now, normally the bank would round your interest to the nearest penny, but we want to keep all the digits just for accuracy reasons. So then at the end of the year, we'll have 1030.301 times 1.01 to the first power. And that's going to bring us to 1,040.604, but okay. Again, the bank would round it to 1040.60. So you can see, just by looking at it, that while the simple interest, wait a minute, what's just happened here? So that means that the total interest now is 40.60, The simple hasn't changed. It is completely independent of the compounding frequency. And that means the compound interest is now 60 cents. And if I keep increasing the number of times a year that I am paid interest, the compound interest will continue to grow, which means the future value will also continue to grow. The simple interest never changes. So because the total interest is the sum of simple and compound interest, if the compound interest is growing while the simple interest is a constant, the sum of the two will continue to grow as I keep increasing the compounding frequency. Now, it's obviously very awkward to have to go through and calculate every single interest payment. So we can take our formula and make a key adjustment to it to avoid doing this every time. And what would that key adjustment be? Here it is right here. All right, so why don't we redo that last problem using our powerful formula instead of calculating the interest every quarter during the year. So what's new in this formula is this letter M. M is the number of compounding periods per year. All right, so just as a quick example, with annual compounding, M is 1, of course, because you get interest once a year. With semi-annual compounding, M equals 2. With quarterly compounding, M is 4. And then you could have monthly compounding. M is 12. And then finally with daily compounding, M is 365. Okay, now you could in principle have other compounding frequencies, but this is normally what you would see in the United States, at least. It would be one of these. And if you're wondering, if you go to your local bank and ask them, they'll tell you that for a savings bank or a commercial bank where you're keeping savings deposits or checking deposits, they're going to compound their interest on a daily basis. That is the normal practice in the United States. Now, there could be financial securities trading in the marketplace, which we'll be looking at later on, that do have different compounding frequencies. In fact, we will see some of those when we start looking at futures contracts and forward contracts. But for normal daily transactions that you would make, you can expect the compounding to be daily. Now, why don't we revisit this last case with quarterly compounding? So what you're going to see here is that P is 1,000. R, remember, was 4%. It's a 1-year investment, and M equals 4. So your future value is 1,000 times 1 plus 0.04 over 4 to the 4th power. Well, it's actually 4 times 1, I should say, but it's just 4. And so that means what you're basically doing here is taking 1,000 times 1.01 to the 4th power. And let's see what that gives me. It's exactly the same, of course. 1040, we'll round it to 60 cents. And so that's how you can calculate the future value of a sum with compounding that is greater than 1 year, more than once a year, I should say. So it's not a horribly complicated formula. It's a little bit more complicated, but this will give us whatever we need for any compounding we may encounter. Now, what's interesting about this is now there's an Excel spreadsheet here that I set up called Section 1. And on sheet 3, you can see it looks like we have the exact same example here, except there's a typo. No, there's no typo. Sorry. No, I'm sorry. This is a slightly different example because here we're assuming it looks like it's $1,000, 4%, but it's 2 years. Okay. So M is here. This is the compounding frequency. So they're labeled annual, semi-annual. You can see the M is 2, quarterly, and monthly, and daily. And so what's happening here is that the same formula is being applied. And at the bottom of each column, you can see the future value, total interest, which is clearly the future value minus the principal, the simple interest, which is the product of the rate times the number of years times the principal. So in other words, the product of these three is $80. And whatever's left over, if anything, is your compound interest. So then I gathered everything up over here on the left in a very convenient chart form. And if you notice, every time I increase the compounding frequency, the compound interest does go up, but the rate at which it increases is decreasing. In other words, over here on the right, you can see that if I were to plot the relationship between the compound interest only and the compounding frequency over here, you can see that the curve is increasing at a decreasing rate. Okay, in other words, while the first derivative is positive, the second derivative is negative throughout the entire curve. Okay, and in addition to that, there happens to be a horizontal asymptote to this function where as m approaches infinity, if we were to take the limit of this function, let me copy this into the notes. So here's the formula again. Well, it turns out that this is equal to P e to the Rn. Okay, because of course, oops, sorry. No, hold on. This is just R. And then if you have another exponent here, and of course, since we have a constant P, you know that when you have a limit like this, you can just rewrite it like this. And then, of course, since the limit of that expression is equal to e to the Rn, that implies that our final result is Pe to the Rm. Okay. All right. So in the limit, if the compounding frequency approaches infinity, then the future value is very easy to calculate. So in this case, here, when remember before the principal is 1,000, it's 4%, 2 years, then the future value is going to be so it's going to be 0.1000 e to the 0.08, and that's going to leave us with 1083.28. Now, if you go back to our original example up here where we had a 1 year investment, I've already gone ahead and done this for you. You can see here it's 329. Okay, so that's why this is the asymptote of this function. 329 is the limiting case of how much compound interest we could earn under these circumstances. Yeah, and here I reminded you how this works with the limits. So this has a special name in finance. This is called continuous compounding because we're assuming that the time between well, the number of compounding periods is infinite, which means that you're getting interest compounded or credited to your account at every instant in time or on a continuous basis. So this is referred to as continuous compounding. The rest of the cases are said to be discrete compounding because the number of compounding periods is finite. Okay. So remember the word continuous means an infinite number of possibilities. Discrete means a finite number of possibilities. So when you have in the limiting case is what's known as continuous compounding. Now, you might not think this is going to happen in the real world, and it probably isn't. The reason why this is so important is because algebraically, there's some very important benefits to using continuous compounding. Hull's book. Okay, so in the limit, the future value is 1083.287. Now, if you look carefully at this spreadsheet, you'll see that as we predicted earlier, as you continue to increase the compounding frequency, the compound interest that we earn will continue to increase, but the rate at which it increases is slowing down. And so eventually we'll reach this limiting case, which is in this example, 329. So you're probably wondering, well, do we ever see continuous compounding in the real world? And the answer is no, not really. But it turns out that by convention, at least derivatives pricing models tend to be based on continuous compounding. And it's really more for algebraic convenience than anything else. Now, you might say, well, isn't that unrealistic then? Well, the reality is that no matter what compounding convention we choose, we can always convert one to another. So in other words, if we use continuous compounding in a model of some kind, we can convert the results into another compounding convention very quickly and easily. The bottom line here, though, is that earning a rate of return that is discretely compounded and continuously compounded, there's going to be some rate at which the two are equal to each other. So let's, just as a quick example of this, imagine you've got, well, let's say you buy a stock. and then sells it for 110. What kind of rate of return does this represent? Well, the rate of return with discrete compounding can be expressed like this. So this is the price of an asset at time t. And then t plus 1 just means the next period, which could be the next day, the next week, the next month, the next year. It depends on the application. So this is the price of an asset, one period in the future, which we're going to call time t plus 1. So in this example, we start out with a stock worth $100, and it grew to 110, and then we sold it. Very wisely, I must say. All right. Oh, I almost forgot. We still need to subtract 1 because we're going to end up with 1.1 minus 1, which is 10%. Okay. So the 1.1 actually represents the future value of your investment. When you subtract the 1, it becomes the rate of return. So that means over that one day, we earned a 10% rate of return because the value of the asset increased by 10%. Now, what if we were using continuous compounding? Instead of calculating the rate of return as the ratio of the two prices, we would instead take the logarithm of that ratio. And then we don't need to subtract 1. So in this case, we would end up with all right, so if you pop that into your calculator, you'll see that that gives us 0.0953. So in other words, now it's the same investment. It's the same, you made $10 in both cases, and yet the numbers are very different. So what you're seeing here is that the annual rate of return, or actually, yes, the actual rate of return, it's not annual, the rate of return with discrete compounding is 10%, while the rate of return with continuous compounding is 9.53%. If I were to take, in both cases, what this is telling me is that the future value of $100 is 110, whether we use 10% with discrete compounding or 9.53% with continuous compounding. They mean the same thing. So we can actually use either convention in our pricing models because it's easy to convert one to the other. So in other words, if I'm using continuous compounding in a pricing model of some kind, a 9.53% rate in that model is equivalent to using 10% in a model with discrete compounding. And so even if in practice we don't see actual continuous compounding being used, it doesn't make any difference because we can always take our results and convert them to the equivalent convention that's being used in the real world. So what convention we use will not affect the results that we get. So Hull's book in particular is very heavily based on continuous compounding. And for certain types of applications, the calculations are a little bit simpler using continuous compounding. We'll run into some of those later on. But for now, it's enough to note that we understand how to calculate future values using any compounding convention, from annual to daily, along with continuous, depending on what the circumstances are that we're facing. Now, I do want to point out that if you go back to the slides, we haven't actually mentioned how to use or how to calculate the present value with continuous compounding. So if you look carefully, this is our future value with discrete compounding. Let me copy this in here. And then the equivalent formula for present value is just this. The inverse. That's all it is. It's literally just the inverse. And so you can tell because the exponent is negative. But when it comes to continuous compounding, well, you'll have the same thing. You'll have inverses here. So in other words, if we're with continuous compounding, FV is PE to the RN, which implies that PP must be FV e to the minus RN. They're just inverses of each other. So you can use continuous compounding to calculate either present or future values. All right. So yeah, so they've got some examples here where we're going to see how the compounding frequency is affecting our simple interest, and sorry, not our simple, our compounded interest. So that's actually the example we just saw in the spreadsheet. So we don't really need to go through it again. Yeah, right here. So in other words, here we have separate tables for every possible type of compounding frequency, and we built them together to this little chart. And then at the end, we introduce the concept of continuous compounding. Okay, so that takes care of that. And then here's an example of continuous compounding. Now, what I'd like to point out here is that as we continue to increase the compounding frequency, the present value will actually go down. Okay, so in other words, here we have a situation where the future value is $1,000 and the interest rate is 6% on an annual basis. And you can see we have all these calculations for different compounding frequencies. This is a 4-year investment. So in the first case, we have annual compounding, semi-annual, quarterly, monthly, and then daily. And you can see the pattern here is that as the compounding frequency goes up, the present value goes down. And eventually we reach the limiting case, which in this case is 786.63. That's our asymptote. And that is the case of continuous compounding. And that's the case where we use this formula. Now, the big question is why? The future value goes up when we increase the compounding frequency, and the present value goes down. So here's what's going on with that. So as the compounding frequency increases, the future value increases, and the present value decreases. I mean, it's clear with the future value why this is happening. The future value increases Because compound interest is increasing. And therefore, so is the total interest. But why is the present value decreasing? Well, we have to remember what present value means. Um, Present value is the amount that must be saved today to be worth a given sum in the future. As the compounding frequency increases, the interest earned increases, and the amount that must be deposited today, therefore, decreases. We don't have to put up as much money if we're going to earn more interest to reach the same goal. Therefore, the present value decreases. And of course, it also makes sense because remember, present value and future value are inverses of each other. So anything that causes the future value to go up is going to cause the present value to go down. And if you also notice, they have this interesting curvature. If you look at the graphs, neither one of them is decreasing at a linear rate. Here, the future value is increasing relatively slowly. The first derivative is positive, the second derivative is negative. Whereas down here, it's the other way around. The first derivative is negative, but the second derivative is positive. Okay, so that's why it has that curve to it. All right, anyway. Okay. Now, in case you're interested, this is a quick derivation of the continuous compounding formulas. If this is your future value formula with discrete compounding, first we're going to do some algebra in here. We're going to rewrite this as now, by the way, why are we doing this? All right, so we know the power rule for exponents. And so m times over r times Rn is equal to Mn, which is the original, if you notice how here the original expression Mn is, or Nm, is the exponent. So we're rewriting it a little bit differently. So what is that going to get us? Well, we're going to let k equal m over r and make a substitution. And you can see where this is going. When you take the limit of this expression as k goes to infinity, this will be e. Okay. So we're actually going to end up with PE to the RN. And that's all there is to it. And then for the present value, we just invert this and we end up with FV to the minus RN. So it's, as far as proofs go, it's pretty simple. I'm sure you've seen much worse in real analysis class, but so that's all there is to it. Now, a lot of financial securities, though, are structured in a very interesting way. Every case we've looked at so far assume that the cash flows were being paid out once. I put money in the bank at the beginning of the year. I have a certain balance at the end of the year. Here, we're changing the rules a little bit. Instead of putting money in the bank, let's say once a year or once, I'm going to assume now that I'm going to put the same amount in the bank every year for a fixed number of years. And that means that what I have is known as an annuity. The key with an annuity is that the payments occur once a year and they all are of the same size. And if that's the case, that makes our calculations a lot simpler than they would be if the amounts were different every time. So this is an important idea here, the idea of how to calculate or the present value and the future value of an annuity. And so we'll see later on, bonds, for example, make interest payments on a regular basis, and those interest payments could be construed as a type of annuity. So first things first, there are two basic types of annuities that we may encounter, the ordinary annuity and the annuity due. What's the difference between the two? The difference is the starting point. So for example, what if I won a lottery where I'm being offered 3 cash prizes of $1 million a year, let's say. All right, so that's the prize. It's $3 million paid out over 3 years. And if that's the case, there's two different ways that can be done. Actually, I'm going to rewrite that as 1 MM. You may not have seen that abbreviation before, but 1 MM means 1 million. Why is that, by the way? I have a feeling that it's because M, as you remember from the Roman alphabet, is 1,000. 1,000 square is it's a million. Okay. So anyway, MM stands for million. But another possibility is to do it like this. Actually, I don't have enough room. Let me fix this real fast. What's going to be different this time is that the payments will start right away. So the one on the top, this is the ordinary annuity. And this one is known as an annuity due. Okay. Some cash flows are structured as ordinary annuities, and some are structured as ordinary as annuities do. It depends on the type of security or whatever the case may be. So we just have to be aware that in some of these annuities that we'll be analyzing, the cash flows start 1 year in the future, which makes them an ordinary annuity. And in other cases, the payments may start right away. Now, if you are the investor whoever won this prize, clearly you would prefer the second case because you're getting your money back sooner. But of course, the lottery sets the rules. You don't get to decide how the cash flows are distributed. But so it could be an ordinary annuity, or it could be an annuity due. And the thing is about these lotteries that you see, these enormous prizes, usually when the prize reaches a certain level, they're not going to just write you out a check. They usually will split it up into multiple payments like this. It saves them a lot of interest, that's for sure. So, but yeah, for the very large prizes, this is usually how they're paid out. Now, that means we need formulas then. If we're going to have annuities to consider, we'd like to know their present and future values. Now, you might think that the formulas would be terribly messy compared to the lump sum formulas, but that's actually not the case. Later on, we'll see where these formulas came from. But for now, I'm just going to show them to you. First, here's the future value of an annuity. And notation-wise, this little a is here to remind us that this refers to an annuity, not a lump sum. The other thing you'll notice is that instead of having a P, we have a C. C is the annual cash flow. Again, it's meant to be a hint that this is not a future value of a sum. It's the future value of an annuity. And you can see this is not a complicated formula, especially considering there could be literally any number of cash flows involved. So here's an example. What if we have $1,000 and we put it in the bank every year for the next 4 years? Now we're assuming, you notice how it's written, the way it's written, it's telling us that it's an ordinary annuity, which means the cash flows occur here, 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 and here. Now, you could, in principle, calculate the future value of each cash flow separately and add them up, but there's no point in doing all that extra work because we do have this wonderful formula. And so in this case, we have 4 years, N is 4, the rate is 3%. And by the way, I'm assuming here annual compounding just to keep it simple. Later on, we'll see how to adjust the formula for other compounding frequencies. So you plug them all in and you end up with 4183.63. Now, because you deposited $4,000 along the way, that implies that the interest that you earned must be $183.63. We could, if we wanted to, break it up into simple and compound, but it might take a while. So we're just going to leave it here. It's a little bit messier than when you have a lump sum. Now, this is the future value of an ordinary annuity. But think about this. What if the payments started right away? In other words, what if we had an annuity due? How would that change things? All right, let me draw this into the notes where I have plenty of room. So, and the interest is 3%. Okay, great. Now we've already determined that the future value is 4183.63. If we had chosen to do this with the individual cash flows, we would have done it this way. So the first cash flow is being invested for 3 years. The second cash flow is being invested for 2 years. The third cash flow is being invested for 2 years. And the last, oh, sorry, this is one. I accidentally wrote 2. And then the last one is actually being deposited in year 4. So it's not actually being invested for any length of time. We literally just deposited it at exactly the time at the end of year 4. Okay, so that means this one will be 1.03 to the 0 power. And that, as we've already seen, adds up to 4183.63. Now, what if it's an annuity due? How would it be different? So we start right away. And that will affect the number of years that each cash flow is being invested. So the first cash flow is actually being invested for 4 years instead of 3. The second cash flow is being invested for 3 years instead of 2. The third cash flow is being invested for 2 years instead of 1. And this cash flow is actually now being invested for a full year instead of 0. So in other words, what you're basically doing is taking this result up here and you're multiplying each term by 1.03, okay, because all the exponents are higher by 1. So that means then that the future value of an ordinary annuity, when multiplied by 1 plus the rate of interest, gives us the future value of an annuity due. So we don't have to go through the steps again. All we have to do is take our previous result, which is 4183.63, multiply it by 1.03, the rate of interest, and that's going to give me 4309.14. So it's as if you invested the entire annuity again for 1 more year. So you can see, if you're the investor, the saver, you'd rather have the annuity due. If you're a borrower, it would be the other way around. Now, there is also a somewhat surprisingly simple formula for the present value of an annuity. And that little a there tells me that this is indeed a present value for an annuity, not for a lump sum. Okay, great. Now this formula is for the ordinary annuity. As is this one up here. Maybe I didn't copy it, but yeah, that the formula you're seeing is actually the one that's meant for the ordinary annuity. We have to adjust it to become an annuity due. So let's see, what do they have for us? So how much do we have to invest in the bank today? It pays a rate of 5% of interest in order to generate a stream of payments of $1,000 each at the end of the next 3 years. So we need to know how much will we put away today in order to make sure that we can withdraw $1,000 a year for the next 3 years. You can easily see how useful this would be for retirement planning. Imagine yourself sitting down and saying, when I'm retired, I want to have a lot of money in the bank. I would like to be able to withdraw, let's say, $200,000 a year for the last 20 years of my life. That would tell you how much you have to save now to get to that point. So given that the interest rate is 5%, the C is 1,000 and N is 3, we're looking at all right, just be careful, that exponent is negative. So when you plug those in, you'll see that it's 2723.75. And that implies that the interest that we earned over this period must be the difference between those two, because we were drawing $3,000 on an investment of 27, 23, 25. So the difference between the two must be our interest, or 276.75. Now, the annuity due version, now here's an interesting twist. With the annuity due, the cash flows are invested, or actually, they're withdrawn 1 year sooner. So less interest is earned on the initial deposit. So the PVA will go up. In other words, we need to save more money in order for it to become an annuity due. So more must be invested. And the surprising result here is that the PVA of an ordinary annuity times 1 plus R gives us the PVA of an annuity due. In other words, it's exactly the same as what we had with the future value. I'll just quickly put that back here again. You'd think it would be the other way around, but it's not. And if you look in the slides, you'll see that the amount involved would be and then we multiply that by 1 plus the rate of interest, and we end up with 2859.41. So in other words, that's how much more we would have to save if we needed to start withdrawing the money a year sooner, meaning today. All right. Now, these formulas can also be adjusted for different compounding frequencies. This is the future value of an annuity. The M is our compounding frequency. And this is, and by the way, if you have an annuity due, the adjustment also needs to have this M in the formula. The present value of an ordinary annuity becomes this, and to convert it to an annuity due, we need this. Okay. All right, so here's the derivations. They're not very difficult, which are, well, you'll see when we get to it. It's not very complicated. So, all right, anyway, so I guess maybe we can save that for next time. So we'll derive those formulas, and then we'll move on to something new. And let's see what, we're going to introduce the concept of bond pricing. We have to first discuss what bonds are and how they're structured, and then we'll see how their cash flows lend themselves very well to pricing them with these techniques that we've just been learning. So that's a pretty deep discussion. So I think we'll have to save this for next time. And when we do come back and meet again, we'll first derive these formulas, and then we'll learn about how bonds are priced in the market. All right, so I will see you then.